The laminar flow is the one of two main types of fluid flow. Laminar flow is called laminar or current. The motion of a fluid as is ordered straightforward stuff. In a laminar flow, the fluid moves in parallel planes, and each particle without intermixing fluid follows is a smooth path. Called power line in a laminar flow, the side transport mechanism is exclusively molecular. It can occur in the electric showers we see that have parallel lines. The laminar flow is typical of fluids at low speeds or high viscosity, whereas low viscosity fluids, high speed or high flow rates are usually turbulent. The Reynolds number is an important dimensional parameter in the equations describing under what conditions the flow is a laminar or turbulent. In the case of fluid moving in a pipe of circular sections, the flow will be laminar or since below a critical Reynolds number of about 240. Reynolds number higher turbulent flow can be sustained indefinitely. However, the Reynolds number turbulent flow and the limiting laminar depends on the geometry of system and also the transition from laminar or turbulent flow is generally sensitive to noise and imperfections in the system. The laminar velocity profile has a pipe shape of parabola, where the maximum speed is in the tube axis and velocity is zero at the pipe wall. In this case, the energy loss is proportional to the average speed, much lower than in the case of turbulent flow.
We have this example that is a flow through an annulus, and we are going to have these variables. We have the pressure 0, the pressure L, we have two radius, one is car R and the other is just R, and we have a height of L. To make the balance, we are going to take the areas of the two tubes, and this expression is in the following way. It's 2 times P times R times delta R times P0 minus 2P times R times delta R times PL plus 2P times R by the stress of RC when is in position R minus 2P times R delta R L when R is in R plus delta R. This is going to make the consideration because if we can see right here it's not stress, and in this part it's going to be a lot of stress, so we have to consider the height because the fluid is going up. Also, we can consider the density of the fluid's density 2 times again the area of the tube, the height, and the gravity, and this expression is equal to 0. This expression is going to be divided by 2P times delta R, and this is going to be R times the difference between P0 minus PL divided by L minus R times the difference between the stress in R plus delta R minus the stress in R divided by delta R minus the fluid's density times the gravity times the radius, and this expression is going to be equal to 0. This expression where we're going to have to take the limit to when delta R approaches to 0, and this is going to take this form. We're going to make a substitution of the expression of P. We're going to take this P is equal to P minus the density times the gravity. So the expression, we're going to take out the gravity and the density. So we're going to have this expression So from this expression we're going to integrate, and we have this expression. R times stress is equal to the difference between P0 minus PL divided by 2L times R plus C1 divided by R. This expression we're going to solve by C1. So we're going to take the R times the stress. We're going to make it 0, so we can take this easily. Substituting this equation yields, we have that the stress is equal to the difference between P0 minus PL times R divided by 2L times the difference, of the radius that we express in this way is R divided by R, capital R, minus K squared times the R, capital R, divided by the R. We have the expression for the stress. So applying the Newton's equation, we're going to have, the Newton's equation is the stress is equal to minus mu, the derivative of the velocity with respect with the radius. Okay. And now we have this expression that is a velocity because we're going to make it solve it for v. So we integrated and we have this expression. So we are going to now solve this equation for C2, and after studying and making all the process, we have that the stress is finally the difference between PO minus PL divided by 2L, 2 times, the stress is going to be the difference between PO minus PL times R divided by 2L times the difference of R divided by capital R minus 1 minus K squared, divided by 2 logarithm of 1 divided by K. This times R, capital R divided by R. So this is our stress in our system. And now in the velocity we have that is minus the difference between PO minus PL divided by 4 mu L times 1 minus R R divided by R, capital R, squared, minus 1 minus K squared divided by logarithm of 1 divided by K, logarithm of R divided by capital R. So this is our velocity, our general equation. So until now we finished with our exercise. So hope you understand. Thank you.